Hey, sorry, that video got interrupted there for a second. Well, you don't know what video I'm talking about because I just deleted it. So this is 10-5, some of these even numbered problems. I had got this far and then I just had to stop the video. So it's only 2 minutes in, just decided to start over. So number 6, have this by the limit comparison test because that's basically the same as a 1 over k if we ignore coefficients and just highest power top and bottom. This behaves like 1 over k, which diverges because it's the harmonic series. You could also say here, instead of saying that it's the harmonic series, you could say because it's a p series with a p equal to 1. That works too. So here, this is actually exactly the same reasoning. By limit comparison test, this also behaves like the harmonic series because highest power on the bottom is k squared, the top is k squared, bottom is k cubed. I know there's some of you out there who really don't like all this writing because you're like, I thought this was math class, but yeah, I'm sympathetic to that, but seriously, let me get over it. Number 10. That is going to converge. The limit comparison test. This behaves like 1 over k to the 17, which converges. Because it's p series with p greater than 1. All right. Number 12. I'm going to use the ratio test now to determine whether the series converges. And if the test is inconclusive, then say so. It's inconclusive when you get 1, right, at the end. Okay. The details of the ratio test are very important. So the first thing that you need to do, it seems silly to do it here, but we're going to practice because it's going to be important in like free response questions. It seems silly here because the directions are use the ratio test. So it seems silly to say, hey, I'm going to use the ratio test. But we're going to get in the good habit of doing that. You must write these limit statements. Limit as k approaches infinity. Which one am I doing here? 12. So remember the way that we set this up, we do the k plus 1 term. It's like we're doing a geometric series thing, right? We're like taking a term and then dividing by the one before it. So here's like the next term. That would be 4 to the k plus 1 over k plus 1 squared. That's the k plus 1 term. And then I'm going to divide by the k term, which is the same as multiplying by the reciprocal. Right? And then I'm going to cancel stuff out. I'm going to write this every time because it is a mathematically untrue thing to say equals and then have an expression without this limit thing here. And you don't want to go around telling lies, spreading fake news, do you? Of course you don't. We're interested in everything that's true and beautiful in the world of math. And that limit is just like easy chapter 2 limit. Highest power on the top and bottom is 2, so it's the ratio of the coefficients. So this limit is 4. And what does that mean? That means if this number is in between -1 and 1, not including -1 and 1, that means that we have a convergent series. So this diverges. You could say, sometimes I think we're tempted to say that it failed the ratio test. You could say that. What it's really failing is it's failing to converge, right? And maybe just taking a quick step back, that means if you wrote out the terms of the series, this is not a series that has infinitely many things that actually add up to something. So there you go. 14, ratio test. I'm going to find the limit as k approaches infinity of k times 1 over 2 to the k. There's different ways you could write that. I think well, I'll write it like that. Okay, so if we write it like that, I guess I could just do this. I don't have to do the times reciprocal. I can just put it, here's my k plus 1 term like this, and then just divide by this. That works just fine. Okay. And the limit as k approaches infinity, let's see what we can simplify and cancel out. Got a 1/2, right? And there's k plus 1 of them here and k of them here, and then I got my k plus 1 over k. Highest power top and bottom is 1, ratio of the coefficients, so this is just 1/2. So it converges. And 16. Now, I don't know, I'm a calculus teacher, probably knew that. Oops. I know what's going to happen with this one. Do you? This is, if you think about the limit comparison test, like numbers 6 through 10 that we were just doing, this series is going to behave like the harmonic series, which means it diverges. So let's see what the ratio test does, and then we can see if we can say aha or anything like that. Then I'm going to divide, this is the k plus 1 term, and then I'm going to divide by the next, by the previous term, which means this, the original thing, upside down like. And I don't think I really need to do anything like simplify this, because I can see what's going to happen here with this limit. I have this k plus 1 times this. I could FOIL those out, but the highest power is k cubed, and here I've got this thing and times k, so the highest power in the bottom is also k cubed, and I can see that the coefficients are just going to be 1 and 1, so that's just equal to 1, and that is inconclusive. And you're like, wait, but you said that it was going to diverge because it's like the harmonic series. That's true, but this ratio test was the wrong test to do on this one. So I think one of the tricky things about this is kind of understanding when you need to do, when it's appropriate to do which test, and you know, it comes with practice. Of course, I've been practicing that for a couple decades now, so I'm pretty good at it. But this was something that would have been better to use limit comparison for. So, as I go through, I'll try to talk a little bit about developing that intuition for what tests are better in which situations. Oh, this is a good, well, here we go. We're getting into the problems that say here, use any method. So what does that mean for us? For us, basically that means we have the integral test, we have p-series stuff that we can do, which really is going to be like limit comparison and p-series stuff, and we have the ratio test. So limit comparison is really easy to do because you're just kind of looking, you're just sort of staring it down, and that's the first thing that I would check for. So if you just have k, like when does limit comparison work? Limit comparison works when you just have k to some power, k to some power, It also works on things that are like really, really close to being geometric series, but they have like a plus constant or something, kind of like if you want to look in your book at number 7 that we did just recently. That's a good example of that. So this is going to be limit comparison. Why would you write the k first? That was weird. This behaves like the harmonic series. Okay. Number 24, anytime you see factorials, you're looking at the ratio test. That is a fact, not fake news. I don't know why I'm writing down the original thing here. Usually when I do the ratio test, I don't do that, but oh well. So I'm going to do the ratio test, which involves finding the limit as k approaches infinity of the k plus 1 term. Remember what we're doing is we're kind of checking out to see if we sort of think about this as like being a geometric series. If you want to know what the r is, the multiplier in your geometric series, you take a term and you divide by the one before it. I know you're like, you just said that, McGrath. Why are you telling me that again? Because I think it's easy to get lost in the details of what we're doing and forget what we're doing, if you know what I mean. Okay, so there's the k plus 1 term. I replaced all the k's with k plus 1. And I divide by this term, same as multiplying by its reciprocal. What did I put a plus 1 there for? Sorry. All right, I think I'm good there. And then we have to simplify. Let's see. Not optional, writing this limit thing at every step. K plus 1 factorial over k factorial is k plus 1 on the top. Got to get good at those canceling out factorials. Okay, that's that. And then 10, k plus 1, so I got an extra 10 on the top. And then I have an extra 3 on the bottom. And so I got highest power of k is just on the top, so that is blowing up. Bye-bye. So if you look at this thing as being sort of like a geometric series, it's like a geometric series that has a multiplier of infinity. So that is not going to converge. All right. You know, the other thing, the other test that we do have at our disposal now is the divergence test. We could have just looked at this and said, well, let's see, 10, okay, so that's 10 thirds, and then k factorial. So the 10 thirds, that's getting bigger, the k factorial. These terms are not even approaching 0. So if your terms of an infinite series are going to add up infinitely many things, and the terms are not even going to 0, you can kiss your chances goodbye of convergence. And 26 looks like another limit comp. And it looks like another harmonic series like. By limit comparison test. This behaves, you know what I'm going to say, don't you? Like k equals 1 to infinity, 1 over k, which diverges because it's the harmonic series. And what do we have? One more, number 44. I feel like we we need to do at least one ratio test one that's going to converge. Here's our chance. I'm going to do the ratio test on this one because it's got factorials in it. And it looks like it's got a better chance, maybe, of converging because it's got a factorial on the bottom. So let's see. Also looks a little bit complicated. So let's do the k plus 1 term. That k factorial on the top is squared, and that that's tripping me out. So I'm going to write it out like this. This is the k plus 1 term. Instead of writing that squared, I'm just going to write it out twice. I think that's going to make it easier to see how the canceling happens. And then, okay, so what about this 2k plus 1? What happens when you plug a, that's like 2 and then k plus 1, right? So that's when you bump that up, that's going to give me 2k plus 2 plus 2. So that's important. Did you get that right? Right, it's not 2k plus 3. That's not replacing the k plus 1 there, right? So it is getting multiplied by that too. It's an easy mistake to make. And then we're going to divide by the k term. So there's my k factorials. I wrote them out separate instead of writing squared. 2k plus 2 factorial. Okay. Let's see if we can carefully cancel some things out. So what happens when you have a k plus 1 factorial over a k factorial? Well, everything cancels out except for that last k plus 1. So I get k plus 1 and then the same again, k plus 1. And then with the 2's, 2 to the k plus 1, 2 to the k, I got one extra 2 on the top there. And then on the bottom, if you think about what's going on here, maybe this isn't very intuitive to you, maybe not, I don't know. But if you do 2k plus 4 factorial, that's 2k plus 4 times 2k plus 3 times 2k plus 2 times 2k plus 1, and then so on, so all the way down to 1. And 2k plus 2 starts here. So these two things are left behind after we do all the canceling. So I've got 2k plus 4 and 2k plus 3 on the bottom. And that is all the canceling out we can do. And now let's see what my limit is. On the top, I've got same high power. I've got k squared on the top, k squared on the bottom. So it's the ratio of the coefficients. I've got 2 on the top and 4 on the bottom. Also known as 1/2. So what does the ratio test say? Well, this thing behaves as you go out further and further into this series. It becomes more and more like a geometric series with a multiplier of 1/2, and that converges. And that's it.